Hello, everyone, and thank you for joining us today for our Quantum Speaker webinar series hosted by ATARC Global Quantum Working Group. Today, we are very excited to welcome Dr. Fairbolt Kushnod to speak with us today. Dr. Kushnod is an associate professor of electromagnetic engineering, uh, electromechanical engineering at Cal Poly Pomona, with additional roles at Caltech and the University of California. In this talk, he will explore the potential of quantum entanglement in multi-agent robotic coordination and advantage of hybrid quantum classical system in achieving optimal performance. If you have questions, please feel free to use the Q&A feature. We will save the Q&A for the end. So now let's welcome Dr. Kushnod.
Thank you very much, Lily, for the introduction. Hello, everyone. My name is Farbod Kushnod. My presentation is on quantum robotics in terms of research and education. I would like to start with that introduction of quantum engineering reported by National Quantum Coordination Office. Quantum engineering should be established as a new discipline or subdiscipline in engineering schools, which require development of curricula, textbooks, both at undergraduate and graduate levels. And the National Science Foundation also shall award grants for the establishment of multidisciplinary, so that's again what is related to our work, centers for quantum research and education. So these are the things that we are trying to follow. And as an introduction again, rapid advances in quantum technologies such as communication, sensing, computers, and algorithm demand for training engineers in quantum technology, prepare them for their future careers. And also, in terms of the actual work, in terms of research, is integration of quantum technology with classical mechanical system, which will be, we expect to be inevitable. And so in terms of education, our research proposes to extend the mechatronics field, which is also multidisciplinary area by nature, to add quantum-related topics. And also, we also introduce and promote quantum robotics as a new field for research and integration of quantum with robotics domain. So the integration, such as, for example, quantum communication with mechatronic systems, robotics, and autonomous systems, that's what we are trying to do. And again, in terms of education, we try to work on the photon quantum mechanics, such as experimental quantum entanglement, cryptography, teleportation, and so on. And again, integration of also quantum communication with autonomous systems in terms of both education and research. Okay, so let me show you an overview of what we are trying to achieve here, or what we are trying to propose or promote here. So if you think about the classical mechanical system with classical computers, combination of these two are giving us basically the early mechanical systems, and the quantum lead to the state of the art and the cutting edge technology that we currently have. And the idea is, okay, now if we get the quantum, basically the state of the art and the cutting edge technology, and combine them with quantum computers, or in general quantum technologies, not only computers, but then that's what we are trying to address really for future technologies. So what do we really achieve? And in that sense, we can talk about, for example, one area would be potentially quantum robotics. Okay, so therefore we coined the term quantum robotics. I've created this Wikipedia page in collaboration with my collaborators. Professor Clarence De Silva, Dr. Marco Quadrelli from JPL, and Professor Clarence De Silva was one of the leaders in mechatronics field from University of British Columbia, and many other collaborators, which I'll talk about them. For example, Professor Enrique Galvez, who helped also with a lot of foundation of the quantum work that we have. Okay, so in terms of specifically related to our robotics work, so the early work on the drone-to-drone quantum key distribution was proposed and published by Paul Koyat in 2017. And later, one of his PhD students, Andrew Conrad, recently graduated, maybe last 2 years, in the last few years, with his PhD on doing for the first time, vehicle-to-vehicle quantum key distribution and also drone-to-vehicle quantum distribution. There's also a lot of work done on the space, underwater quantum communications, and then we propose the quantum robotics, which is more kind of general of combining the robotics domain and the quantum technologies, and then basically investigating the intersection of those. And then also there's also more work, various attempts on quantum communication by UAVs, more recent work. So these are all very recent. Also in terms of education, so we want to prepare the quantum revolution, and what is the role of higher education. So that's what we are trying to address. There's a publication published in 2020, and also achieving a quantum smart workforce, another 2020, and also building a quantum engineering program, really. So that's, again, another publication, 2022. This is from that publication, Building the Quantum Engineering Undergraduate Program. So in general, this diagram is from that paper, which is showing you what we are trying to do here. And in our case, we are trying as engineers, especially engineers, I'm more relating to engineers who are mechanical engineers, who are aerospace engineers, electromechanical engineers, who are not really traditionally educated or trained in the area of quantum. So we never had a course in this area. But of course, if you think about quantum computer engineers or electrical engineers, they have had some sort of traditionally in some courses related to quantum, maybe optics and some other related courses. But we are trying really to bring quantum to more mechanical, electromechanical, and also aerospace area, which they don't really have this kind of training. Okay, so if we look at the mechatronics course, which is naturally a multidisciplinary field and includes mechanical, electrical, and also structures, programming. So the idea that we had was that we proposed that, okay, so let's modernize a mechatronics course and mechatronics field by bringing different topics of quantum to mechatronics field. So we talked about that, we published it, but also in the past few years, I've been teaching some quantum, fundamental of quantum mechanics in my courses in mechatronics course, which is available. So it's a few lectures and labs, but the way that we approach that is a little bit different from what physicists do that. So we instead of really focusing on the theory aspects of the quantum mechanics, we start with explaining the experiment. And then from the experiment, by explaining the experiment, we try to later on bring the theory in. So by nature, again, engineering students, we feel that they have a better understanding on the aspects of the idea of the quantum if they see the experiment first and understand the theory from the experiment. So we approach it from that angle. And so the things that are related to this mechatronics that can be included in the education can be quantum sensors, quantum networking communication, computers and algorithms, of course. These are the general areas that can be covered. Okay, again, the integration of quantum technology, mechanical system, again, we said that is inevitable with the fast growing of the quantum. So we need to think about how really we can look into the mechatronics of the system. So what is the integration of these robotic kind of combination of these mechanical systems and quantum? What does it mean really? What do we need to do to achieve that or to address that? And we also think that the hybrid quantum classical technologies would be the most kind of practical approach in this field, which is kind of, if you can think about quantum solving some of the problems and classical the other type of problems. So it's a combination of a hybrid system which can be the most efficient. So these are again areas of thinking about what would be the optimized system. So that's a research area that we need to really think about, and we are trying to promote that. So we're asking people to think about that and what do they think we should do. Okay, so in terms of education, I start again with explaining the photon and the polarization, and there's a lot of resources that student can look at online, and videos useful. So polarization can be, for example, what does it mean when we talk about vertical polarization, horizontal polarization, how they are, when we talk about correlation between these two, if they are entangled photons and so on. So we start from that in terms of education, and there's a lot of resources available that you can simulate this kind of representation, for example, polarization or the waves going through polarizers and how the beam splitter works and so on. So these are the main components of a kind of a parametric down conversion experiment that we are trying to do in terms of entanglement. And there's a lot of useful tools, animations that we can use in terms of education that we do for engineering education. Okay, again, some tools that the student can learn about without going too much deep into the what are the optics systems. You're really learning about half-wave plate. What does it do? For example, here you can see that what is the input polarization, and then when you rotate the half-wave plate, what would be the expectation of the output polarization of the wave, and also a beam splitter, polarizing beam splitter, which is if you have an incident, then you can it can pass and transmit the horizontal polarization of the photon and reflect the vertical ones and so on. So these are kind of basics that by learning that, they can start to understand basically what the experiment is. And also talking about the parametric down conversion using the nonlinear BBO crystals, which can give you entangled photons. For example, they're entangled in their polarization in terms of the being horizontal, two horizontal output single photons, or two correlated vertical photons after passing through the BBO crystal. So again, these are the things that we start with in terms of education, and then we look at the overall system, which includes again the BBO crystal, which can give you the entangled photons, and then going through the beam splitters and the 4 detectors that can represent Alice and Bob. One side is Alice, one side is Bob. And then going that through the single photon counter module, and then FPGA to count counting the coincidences between the entangled photons, as well as timing. So basically the timing tell you if the photons are entangled, if they are like in the range of 10 nanoseconds, and so then you can, when you receive them using the single photon counter, then you can evaluate them as entangled if the window of the time when you receive them, they are in the 10 nanosecond range. Okay, so this is an overview of an experiment that maybe I can show you here. So this is a basic setup that includes BBO crystal that you saw, and some, so these are only 2 of the collimators, and you saw, and so 2 of them are connected to this single photon counter, and I show you more power supply. And then this is a tool, LabVIEW tool that developed by Mark Beck, Professor Mark Beck, which is available online. You can you can access that if you need to program your FPGA for counting. So this is a closer look at the similar setup that I showed you the diagram. So half-wave plates, polarizing beam splitters, and then on one side A and A prime for so for Alice side and B and B prime for Bob. And here we have the narrow bandwidth collimators, and then also the filter, sorry, narrow bandwidth filter and the collimator behind that, which is going to the fiber cable to the single photon counter. And here on this side, when the beam, this is the beam splitter, polarizing beam splitter, two of them. So it transmits the horizontal polarization of the photons and passing through that detector on this side, and then reflects the vertical polarizations. There's a kind of overall setup, and this is another view of the same thing, just a little closer view. Again, this is overall basic setup, which includes 405 nanometer, 100 milliwatt laser, and the BBO crystal, which is the BBO crystal is giving you two 810, basically giving you the 810 nanometer correlated photons or entangled photons. Okay, we can also now use motorized half-wave plates, which can be used for automation, automating the communication or entanglement distribution. Also can be used for doing the automated Bell experiment, which I briefly talk about it soon. Okay, so again, a LabVIEW program by Mark Beck, and these are just a single photon counter. These are showing you the single counts and the coincidences in this program, which you can get it from the Professor Mark Beck website. Okay, so this is kind of some of the results as an example. But more recently, we mostly use a MATLAB base by Professor Enrique Galvez developed this software, and he has a lot of useful resources on his page, so in which you can again learn about how to set up the experiment. So here I'm looking at the single photons of A, B, A prime, B prime, and the coincidences here. So we have doubles or the coincidences, entangled photons for A, B coincidences, and A prime, B prime in this case. Okay, so now we also set up some hands-on learn by doing experiments, which is remotely can be automated, so a student could access remotely from home the lab, and using the motorized polarizers, rotate them and do the experiment, collect data. For education purposes, we use quantum cryptography kit from Tor Labs, which is very useful. I highly recommend that for learning, which is very well developed and comes with some very useful manual, which can explain to you Alice, Bob, quantum cryptography explanation experimentally, and the eavesdropper starts with the basic setup of the Alice and Bob and some polarizers, as well as explaining the relation between how you can communicate between Alice and Bob, and then also explains how Alice and Bob can find out about if there's eavesdropper, so they can find out and they can detect that. And so it's explained very well. So in terms of our work, we are trying to basically integrate what we are doing in terms of quantum entanglement or communication, and put them on mobile platforms. So, and then do that while the agents or robots are moving. So we call them a Bob robot, Alice robot, and they're trying to communicate with single photon. So these are some kind of figures, pictures that I show you from some of the past experiments that we have been trying to do it, mostly trying to show you the mechatronics aspects of it. So some other kind of configurations. These are a little bit older pictures. We have newer configuration. They are different from this. So especially that we are trying to automate this, and we are trying to optimize. So optimization is part of our work, has been a part of our research. We also address quantum teleportation, which is the teleportation of the state of the polarization of the photons. And also we did some, we also tried to, you may have seen the controlling of the mechanical system with the brain interface devices and the headsets. So we also integrated that to controlling the motorized half-wave plates, and just as an interesting, some kind of experiment that we can really, just something maybe you have seen in terms of controlling drones using the headsets, but then what does it mean in terms of bringing that to quantum field? But okay, so now one of the challenges that we have is the alignment when the mobile robots are moving, and how do we do that? So this includes two steps of the alignment, which is the coarse alignment and fine alignment. The coarse alignment is achieved by motion tracking cameras, and the fine alignment using fast steering mirrors. Okay, so this is kind of a general representation. You can find that on the Wikipedia. I posted this diagram that I have here. So this diagram showing you that, okay, how you can from the source you can transmit or distribute the entanglement to two robots. Okay, Alice robot and Bob robot. You can come up with a different configuration, which includes the motion tracking camera, and then also as well as fastest steering mirrors. These are the fastest steering mirrors. So you can have a look at that if you're interested. And then we also have the actual experimental setup in the lab, which I'm going also to show that in my workshop next Thursday. There's a workshop, I'll talk about it. I'll show that in more detail. We have done some kind of earlier, before we start the experiment, we did some kind of also implementing algorithms. So for cyber physical security, so how we talked about how autonomous vehicles can benefit from entanglement, for example, in terms of algorithms and path following or navigation aspects. So in this case, we are talking about two robots moving towards each other from the circles and trying to find each other, some kind of algorithms that is from entanglement. And these are two robots, the path of two robots that are trying to push an object in, and how they can, entanglement can help them to achieve this task with minimum information. Okay, so this is kind of a multiple kind of robots, again, algorithm-based only, and how they can follow a path with minimum communication between them using quantum algorithms. And we are also interested in finding basically the integration, which is, for example, what is the transfer function of the integrated quantum and classical system? For our experiments, we look at, again, there are a lot of references from Professor Enrique Galvez, 5 quantum mechanics experiments for undergraduate education. So you do that. This is, you can find also nice videos on how to set up parametric down conversion. Again, Professor Enrique Galvez here. He has remote also set up that you can access his lab and perform experiments. We also have done similar things. The last thing I would like to talk briefly is that we did also Bell's experiment. So Bell's experiment, which is now CHSH, is one of the versions of that by John Clauser and his colleagues, who also won the Nobel Prize by doing this experiment in physics. So it basically you can validate your experiment. So you can validate that, okay, what you're doing in terms of quantum entanglement is valid by showing the Bell's, doing this experiment and getting the result from that. But also it is a fundamental proof of that entanglement of about entanglement, which is not classical. So that's a proof. So basically, you rotate the half-wave plates with different kind of angles and perform some experiments, and you do multiple tests, and you can show that that entanglement, for example, the probability of doing quantum experiment in achieving some result, you may be able to achieve something that classical can never achieve that. For example, if you are designing a game that has a maximum possibility of winning in classical game with 75% possibility, then you can design an entanglement-based quantum experiment that can go up to 85% winning or achieving the goal, which is much higher than classical. Okay, so we did that experiment again in collaboration with Professor Enrique Galvez, and we showed again this S value, which is a value that shows that if you achieve 2.7, which is higher than 2, then that shows that your entanglement is valid and your results are valid, but also is a fundamental experiment that shows you about the possibility of achieving 2.7 compared to classical limit of 2. Okay, so I briefly would like to also at the end invite you to a workshop. It's called Quantum Engineering Workshop. We have done that. This is the we are doing now for the 5th year at Caltech. We have had many world-renowned experts and speakers, distinguished speakers in our workshop in the past 4 years, and this year we also have more speakers, distinguished speakers. So last year again, we had Dr. John Clauser talking in person at Caltech. He also was remotely. The videos are also available online if you like to see them. They are very interesting talks. Feel free to look at them. So this year, this is the 2025, next Thursday on 29th. We have again distinguished speakers, world-renowned experts from Caltech, University of Chicago, national labs, JPL, University of Colorado, UCLA, and many other distinguished speakers, Australian National University, which they are doing also a lot of interesting algorithm in terms of that we can use in terms of quantum control of the systems. Okay, so at the end, I would like to invite you to join us on May 29 for the 5th Quantum Engineering Workshop, which is in person, as well as a remote, which is a free event and is flexible. And thank you for your attention.
Thank you so much for this presentation, and to all of our attendees, when we send our follow-up here, we will make sure to include a link to join this event that we're talking about. So unfortunately, we don't have time for any questions today, but again, I want to thank you so much for
I just want to mention, sorry, before interrupting. So one of the things that I think is important to mention about the reason that we are doing all this work, of course, I mentioned about quantum cryptography, but the main reason is for security, because quantum provides guaranteed security and also which is not achievable with classical. Classical can also improve the security to some limit, but the only way to achieve guaranteed security, and it's becoming more and more important, for example, cybersecurity and so on. So this in robotics domain becoming more important to achieve that by using quantum. Okay, thank you.
Very good. Well, that concludes our webinar. Thank you so much. We'll see you next time.